Check, check. Good morning, everyone. Welcome to Saturday at DragonCon. Ooh, 10 a.m.
You're so excited.
Yay!
Who's here for science?
Yeah.
Wait, this is science?
Oh, no.
Those costuming.
Yeah, this is science. If you don't want to be here, if this isn't your room, well, too late, you're here. Before we begin, again, if we ask, please leave your mask on for the entirety of the panel. Try to prevent spread of nasties. The second thing is please remain in your seats. Don't eat in the panel room. If you need to take a sip of water, do that, but please keep the mask on the whole time. Again, this is for everyone's safety. Second, please keep your cell phones on silent. Some of the big things that are coming up today. Our first big panel is down in the Crystal Ballroom, Paleontology Hour at 1 o'clock, which is going to be awesome. Another cool one later tonight at 10 o'clock is Solve for X. If you want to see scientists be really uncomfortable, we got some good stuff there as well. Last thing I want to mention is our charity Open Hands. DragonCon's matching dollar for dollar for the first $10,000. Help us make them pay. Please donate. The charity is giving nutritional rich food to those in need and make sure they be able to live long and healthy lives. With that, I'll turn it on to Stephen.
Thank you so much. Do you know what panel you're at?
No.
Yeah, everybody's looking very blank. Also, just to let you know, we are going to unmask so that folks who are hearing impaired will be able to lip read. Just wanted to let you know why we are not doing as we are saying that we are doing, so that the microphones can hear us and people can lip read. I am Stephen Grenade. I am the director of the science track, and welcome to the hard science of future space travel.
Oh, right.
Always fun when my panelists are like, oh, that's what I've signed up for.
Yeah, right. Yeah. Oh, boy.
So we'll start on the far end. I'm going to mix things up. Andy, if you will start and introduce yourself and say what it is that you do.
My name's Andy Dykes. I hail out of Northern Virginia, just 2 blocks inside the Beltway. I work at L3 Harris. It is very strange for me to be here at DragonCon on the space and science tracks, and my current job leads a software development team. Like, what? But for the first 15 years of my career, I flew satellites for both NASA and Intelsat. I got to support, I think, 12 shuttle missions while I was at NASA Goddard, which is fantastic. It's one of the highlights of my career, and it got lucky that it was early on. But then I moved to L3 Harris after 10 years of flying commercial satellites to be the space guy that tells the coders how to space right, you know? And then somehow I'm all of a sudden managing people. I don't know how it happened. I really don't. And I don't code worth a lick. But I did want to, while I'm on Meet, give you an Artemis update because they're 2 hours behind loading liquid hydrogen because of a leak on an 8-inch connector between the core and the mobile launch platform, and they're going to try again to allow the cryo connector to warm up before they.
I like how that sunk in. It just
They're going to let it warm up, so it's kind of like turning it off and then turning it back on again for cryogenics, I guess, and it's leaky, so they hope it'll expand, I don't know. But I'll keep you updated if anything exciting happens.
Oh, is it?
No, I mean off the deal.
Yeah.
Hi, I'm Rob Hampson.
Eat the microphone.
Yeah, I got to eat the
Yes, there you
microphone.
go.
Yes, sorry. Ice cream cone. I'm Rob Hampson. I am a physiologist and pharmacologist by training, a neuroscientist by practice, and for the most part, my field is memory. And everybody says, "Oh, I need that."
Thinking the words.
Yes. But I got involved with. I've always been a space fan. I've always been a space nerd, and I got involved with reviewing projects. Program projects and proposals for NASA and the National Space Biomedical Research Institute, NSBRI, back when it was a NASA contractor. And that got me also to the attention of a group that was originally called the Tennessee Valley Interstellar Workshop and then changed its name to Interstellar Research Group. And we put on a workshop every 2 years or so, and I've been on program committee bringing biology to all the engineers.
Thank you.
Hey everybody, I'm Bob Novella, co-host of the Skeptic's Guide to the Universe podcast for an obscene amount of years. I just lost track how many years it's been now. Also, Alpha Quadrant 6 podcast and co-author of the Skeptic's Guide book and our second book that's just coming out in a few weeks, Skeptic's Guide to the Future.
I'm Chuck Gannon. I lie for a living. That means I'm an author. It also means I'm a liar, but what the hell?
Welcome to 10 a.m., everybody.
Yeah, right? But I'm here all morning. So at any rate, I'm probably most known for hard science fiction, where I define hard as anything that mother or father or whoever nature has essentially not disproven is something that's fair game, at least for exploration. This series started with this. The current one, Fire with Fire, this was a Compton Crook winner. Nebula finalists. There were
Show the
4.
other side of the room.
Huh? Sorry.
There you go.
Yeah, and I
For me,
obviously
really.
I got a huge image here for this. But they're portable, so there we are with space again, right? And then the current one is this one, Mark of Cain. There have been 4 in the series that were Nebula finalists, Dragon finalists, et cetera, et cetera. My day job, so to speak, is the writing. One of the other things I do, and if Greg shows up, there will be 3 of us on this panel that are members of something called Sigma, which is called Science Fiction in the National Interest. It could also be called, here's how Arlen Andrews, who is our founder, herds cats. The laughter is knowing, and so I'm here in that component. I've pretty much advised, I think, every space-related agency except for the newly founded Space Force.
I'm Stephen Grenade. I am a physicist. Most of my work and research focuses on sensors. I have tiny mirrors on the back of Hubble. It's on Hubble's butt. It's really cute.
Hubble butt.
And
Hubble butt. I
yes,
love it.
yes,
Sensor.
Not bubble butt. Hubble butt.
Hubble butt.
Yeah.
And have a great interest in how do we see things when we're out in space. And so I'm very excited to talk about this. And I want to start. We're going to start sort of close to our current time and move further forward in the future. We will be moving into the future faster than 1 second per second. But I would like to start by asking, all right, let's go to space now. How do we do it?
Well, I guess that's me, huh?
It could be any of you.
All right. So we're to clarification. Are we talking about crude, or we're talking about crude spaceflight, right?
Yes.
Okay. Good. Okay. I like.
We're going to send squishy humans out into space.
I'm sorry. I just spent 2 hours answering questions across the hall about space. So anyway. So orbit. The way that orbits work is you accelerate something really fast, actually horizontally. And you get it going fast enough that the Earth, being round, not flat, we checked. Not being round, we go fast enough that the rate of acceleration down towards the Earth is outpaced by your velocity going forward. And so you start falling around the Earth. Now, to do that requires a lot of velocity. I like to use the International Space Station as an example. It's at approximately 250 miles. It varies, but it's at 250 miles above the Earth's surface. That's basically the straight line distance between Washington, D.C. and New York City. Not that far, right? It's going 17,500 miles an hour. If you want to know how it got there... Also, wow, I just realized we're counter the parade, and y'all are here. Yeah, okay, sorry.
Thank you.
Science! If you want to know how the International Space Station, most of it got there, there's a panel Monday morning at 10 a.m. It's a solo panel by one Andy Dykes on the legacy of the space shuttle. Yes, and it's across the hall. But the point is that it takes a lot of momentum, a lot of propellant to get going fast, and it takes a lot of propellant to get to slow down as well. So getting to space, just getting into space off of Earth is hard, and I could talk about this for the entire time, but I'll stop.
You cannot, actually. But I appreciate the offer.
I am able to, but I won't.
So once we're up there, how do we stay there? How do we live there? What are the things that we need to be concerned about if we're just going to be hanging out in space? Rob, I'm looking at you. I know you have some thoughts.
Oh, yeah. So one of the one of the cautions I've been sounding for years is that for years we've known that we need to do something about gravity, and we still have not
Do
put
something about it.
a centrifugal habitat up in space, because there are a couple of things we don't know. Stanford Torus is what, a 1 kilometer radius?
Mile, I think.
1 mile.
One
okay,
mile.
1 mile.
One RPM.
use
1 mile
miles.
equals 1 G equivalent.
1
as
G
I recall.
equivalent. That's actually really, really narrow, and our inner ear is very, very sensitive. And if you're facing the direction of spin, and you turn your head, your inner ear just says, "Man, you just accelerated worse than any roller coaster." And now there's ways to adapt that out, and we have some pretty good theories that will work, but we don't know because we haven't tested it. Because any centrifuge tests we've been operated on Earth have been much smaller radii, and the person is fixed in place. And has anyone here ever ridden mission space at Epcot, Walt Disney World? Yep. What do they tell you?
Don't turn your head.
Don't turn your head.
Is that what the centrifuges?
in centrifuges
Yeah.
in general, that's
Yeah.
one of the major principles. Don't turn your head, and so it's
Can I
one
add
of those
one
things.
thing before you leave the centrifuge?
Yeah.
What? Which is you're still doing it in a 1G gravity well.
Yes,
Right.
exactly.
So you really don't have a test.
The other thing we don't know is we're looking at what 0.37 Gs on the surface of Mars. We're looking at about 0.16, 0.17 Gs on the surface of the moon. We don't know what long-term consequences are going to be. We know that there is a lot of physiological breakdown that occurs with prolonged 0G exposure. But what about 1/6 G? What about 1/3 G? We don't know yet. So as far as bio and what it takes to live up there, we need to get up there and do it. That's really what it amounts to. We got to get up there and do it. And that's my bio lecture for the day. We just have to get up there and do it because there are so many unknowns that the only way to figure that out is going to be
Do it.
Can I tell you something?
Yeah, absolutely, please.
Radiation mitigation is a major issue.
Huge.
You have the other issue. You have a lot of other issues. Bioloop is not just something for spacecraft. That is ultimately going to be, for any foreseeable future, it's going to be imperative for whether you're talking about on some geological object or a space platform.
Can you unpack that?
Yeah.
When you say Bioloop,
Bioloop, in other words, so in this room there's a lot of biomass, and there's some water and there's lots of air. Now the question is,
talking about y'all.
if the suit fits, wear it. At any rate, what the idea is, how would you build a system? And we also want to have food in the room too, and everything else we need. How do you build a system so that all the biological elements are essentially at almost a 100% self-replacement efficiency level, through whether that is through processing, whether that is through hydroponics as a sort of add-in. There's a whole how you refilter the water successfully enough which is really, that technology has come way far. Just in the time I've studied it, people going from like to actually saying I can't tell the difference. They've done tests, so that's what I'm talking about Bioloop.
So can you use the maybe non-peoply biomass to help with the radiation?
As a matter of fact, well, this is. I was going to save that because it really gets to next order issues. Let us say that we are now talking not merely about visiting space, but living in space, and now living in space for extended periods of time. If you are doing that, you are turning around something that we currently don't have. Every consumable that we have, every volatile, is coming from planet Earth. That's a problem. The moment you get upstairs, you now get to a place where there's actually a lot of water in this system. And one of the interesting things, as submariners will tell you, is the shielding of water. Like 1 meter of seawater is huge against cosmic rays. And so one of the things that you hear all these debates going on about, well, people are going to die from gamma rays and cosmic rays. Well, actually, when you start thinking about having water, you're going to want to carry water with you. That's going to be one of the major parts of your Bioloop. And one of the places you may put it is actually in segmented baffles on the outside of your ship. Because then, and you don't need to have it all over your ship. It's just, where do you sleep? Where do you spend most of your time? So it's engineering, it's access to resources, which is, like I said, I was leaving that for the, now that we're living in space, part of this.
Well,
It's all
Part of the problem, though, you got to get the water into space.
that's exactly what I was
The
about to say.
expense right now is still ridiculous, and that's the hugest problem about that. We need to look at other ways, that aren't going to cost $10,000 per pound or whatever that number is now. You use the word impediment. For me, I look at it from just pure technology. What's the rocket technology going to be like? And we need to talk about how we get into space now. Chemical rockets, and they're fantastic. They've done an amazing thing for the past half century. But in the future, for long distance travel, they suck hard, really bad. Here's
And
the
why
best
is that?
example. Here's the best example. Tsiolkovsky rocket equation is the answer to that. But here's the best example. You want to get a toothpick to Proxima Centauri in 100 years, and you want to stop there and deposit that's your cargo. Just a toothpick in 100 years. If you plug those numbers into the rocket equation, you will need the chemical and energy equivalent to 10 to the 2200 times the mass of the observable universe. So for long distance traveling,
So it's a challenge.
chemical rockets
At that
are
point, it's
not.
just engineering.
They're not the answer. Chemical rockets, and we are finally moving away from chemical rockets. We had the technology in the '60s, but the shuttle blew that out of the water. So now we're finally developing it. Now we're going to have a nuclear rocket in space relatively soon, and of course we're having it there for the wrong reasons, because it's like we need control of cislunar
Cowboys.
space between the Earth and the Moon, and we got to beat the Chinese there, so we got to have nuclear rockets, because if you're going to dominate cislunar space, you need to get material from A to B very quickly, and chemical rockets are not going to do that. Nuclear rockets are much better at it. So my discussion here is going to be will evolve talking about the rockets beyond chemical. What's beyond chemical that's far superior for traveling long distances within the solar system?
Ooh, I
Pretty
got
much
one.
everything.
I got one.
Yes.
Can we go on another propulsion system? Can we go into propulsion systems, Stephen?
Sure.
All right.
Oh, we are. I will.
Yeah.
And we'll be getting to questions.
I'm here.
So working at Intelsat, it's commercial telecommunication. Almost all the 75 satellites that they owned, and definitely the 14 that I flew at a time. That's fun. My flock are either are chemical or electric. Now, electric is great once you're in space. It's not good for getting off the
So
Earth.
can you explain what you mean by electric?
I will. Yes.
Awesome. Thank you.
Yes. So consider you're in space, and you want a way to accelerate that doesn't use necessarily a whole lot of mass. Well, you got to keep in mind that thrust is merely a change in momentum, mass times velocity, right? So if you send a certain amount of mass at a certain velocity out of the spacecraft, the momentum is conserved by accelerating the mass of the spacecraft at another velocity to make it all even out. We do that with chemical propulsion. You've seen that to make things really hot, to increase the pressure, to increase the speed out the nozzle. For the electric propulsion, instead what we do is you take a noble gas like xenon, usually, and we have good solar panels and good batteries, and we take a xenon atom, we strip off the electron, we then take that positively charged atom and accelerate it through an electric, three electric screens, an electric field, and it zips out the back of the spacecraft. Now, that doesn't seem like a lot, right? An atom. But you do it, trillions, uncountable numbers of times, and that's a small amount of mass, but it's going really, really fast, and it's very efficient because you can pack a lot of xenon into a small tank, and it doesn't weigh much.
ISP is crazy.
And then one other very key component is that you give it the electron back once it's out. Because otherwise you make plasma, and then you get shocked, and that's no good. So for you Star Wars fans, twin ion engines?
Yeah.
TIE fighters? Yeah, no, that's not how that works.
Because
They don't go that fast.
Because in addition to everything else you need for it to be operationally significant for 90% of the needs we're talking about, you need lots of time.
Yeah, it's slow. It's incredibly efficient. Low thrust, opposite of chemical. It's opposite of chemical,
Exactly.
which is inefficient but high thrust.
So not great for humans, but good for like cargo and things and probes that don't mind spending a lot of time.
Pre-positioning caches, whether those are stationary, whether
Right.
those are down
Right.
a mission
Yeah,
track.
let's talk about logistics, right? Because
Yeah.
if we're going to be up there and there for a while, where do we get our stuff? They've got no answer to this,
There's
folks.
Oh no, I just
Mostly
didn't.
from Earth for a long time.
I'm trying to shut up.
Isn't there an ISRU panel?
I'm
That
sorry?
may be a space track thing, but there's an in situ resources utilization panel at some point, which is exactly, like if we're going to planets and stuff, that's what we're doing, but not when you're in space, unless you have a Broussard ram scoop.
Right.
Star Trek, the red things on the front of the nacelles, scooping up hydrogen, making antimatter. Come on, folks. Antimatter, that's what
It
we
is
need.
10 a.m. Give us a break.
I've been up
Grief.
since 5:30.
So are we still in thrust? Or are we in the broader aspect of logistics? Period.
As you see fit.
Okay.
As you are
so
interested in talking.
First of all, if you've got a consumable in any sort of sustained presence in space, the more you want to, the more people you want to sustain, the more operations you want to sustain for the longer period of time, the more you really have to be living off the spatial land, so to speak. That's both volatiles and non-volatiles. So running a fast list. You're going to want reaction mass from the frontier, which means all sorts of possibilities. As a matter of fact, the moment you're into water, you're already halfway to some of the fuels, depending upon your propulsion system. You're going to need remote vehicles. The only ones you're going to be streamlined are the ones that actually have to interface with an atmosphere. Otherwise, they're a damn waste of time. You want to think about carbon processing out there. So it's not, everybody's always said get that iron nickel asteroid, that's where it is. Well, when you think about it, iron and nickel is heavy, it's great, it requires a lot of heat. If, however, what you can do is look at carbon filament and in general carbon compound processing, in some ways that will be more friendly for a variety of reasons, which that's a longer conversation. And automated support and replenishment are really important, and caches, and which could be for mission specific or general, in the sense of there have been a lot of military operations, and what they do is they say, we think we're going to be there, so since we think we're going to be there, let's create a logistical checklist of stuff we are going to cache there as an emergency need if we have to reroute through that area. All of those sort of things are going to apply in space as well. And now I'm going to shut up.
Speaking of like living in space, Rob, I think you had brought up the heat management issue. Isn't space cold?
Space is cold, but the problem is that you don't really get a lot of heat transfer. You can radiate it, but I mean, this is a thermos bottle. Yes, I have my hot coffee with me. This is a thermos bottle. What do we use to keep it hot? Vacuum. Yeah. So aside from radiation, we really need to do a lot of heat management. And one of the things I actually loved about the Expanse series was the fact that Ceres was hot and humid and dripping all of the time, because that's what a lot of our space habitats are going to be like. The body heat that we give off is going to accumulate. And we're going to, and of course, all of our machinery.
Electronics, yeah.
All of our electronics. And by the way, the electronics which don't like water, that are going to be covered in condensation and lichen and mold and all sorts of wonderful things like that, which, by the way, certain lichens and molds live in vacuum and hard radiation. So heat management is a major issue. Now, one of the great ways to do that is grab some ice from a comet and pump your heat into the ice and melt the ice, and now you can use the water. And then you can, if you've got a plentiful supply of water, then if you keep getting more asteroids or more comets, then you can pump all your heat into the water and throw the water overboard. Not that you want to, but you could.
We did with shuttle.
So a couple of other things is recapture. if you can recapture heat, you are then making sure you're not doing energy. You're not doing work that you need to do twice over. And some of the basic things of that is take a look at any geothermal system. It would need to be modified, but a house on a geothermal system is from a paradigmatic standpoint kind of a view forward. If you've got enough heat and if you can concentrate the heat, you can actually turn turbines. And that's another opportunity. The magic bullet to all this is a very, very threshold science called thermionics, which is it's sort of one of those, 30 years from now and we'll have it. But this is where you're taking heat and you're finding a way to directly transfer it into energy. If you can do that, which is like playing some major stuff with physics that goes all the way back to, who am I trying to say, Maxwell. Clerk Maxwell. If you can do that, and there are some indications that you could, we just don't have that material yet, and we don't have that understanding yet. That would be huge because it means the humans become in that community become part of the energy to propel the Bioloop. I mean, there are answers, but they're not at hand yet.
Does that then start to break down with either population increase or decrease?
It break down in terms of what?
Like working. Like if you said
no, so you'd need to know what the materials are, and right now they're still very much in. Every time there's a development on the quantum horizon, every time there's a development that will have to do with graphene, you look at somebody immediately turning around and saying, so what would that mean in terms of a genuinely thermionic subsystem, which might not be it probably is going to be a cascade of things. And until you know what it is, you're not going to know the answer to that question. But it's a really important question.
Yeah.
So I'd like to back up a second. Bob, you had brought up nuclear rockets. Can you explain what the hey?
Yeah, it's just, to me, it's just so obvious. We're heading towards nuclear rockets where we have them now. And for me, in the foreseeable future, I'm talking centuries, of course, excluding the creation of an artificial superintelligence, which means everything we're saying might go out the window in a lot of ways. But without that sort of godlike help, fission rockets, I think, we're going to be tweaking them, especially fusion rockets, I think for centuries. For centuries, this is what we're going to be working on. This is how we're going to get around our solar system. And it's essentially... nuclear energy is 10 million times more efficient than chemical energy. The energy is there, but that doesn't mean the performance is going to be 10 million times greater. I mean, reactors weigh a lot of money, weigh a lot.
Deal with that too.
The weight's a killer. But
so what you're suggesting is radiation both inside and outside.
Good radiation.
Good radiation.
So with a nuclear thermal rocket, we're talking. The exhaust velocity is about twice as fast. Ship time, travel time is about half, and that's for the very first nuclear thermal rockets that we may see, and that's the very beginning. Eventually, when we get to fusion rockets and we start tweaking them for God knows how long, we could eventually maybe we'll get to the the most efficient, which is hydrogen proton, which is like the exhaust velocity is something like 11% the speed of light, which means we could potentially get to 10 or 20% the speed of light using fusion, the most efficient form of fusion. But then the next level, and I think we will eventually get there. Who knows how long that's going to take? That could take a century or more. But I think that's how we're going to be traveling around our solar system. But if you want to take it to the ultimate expression of a reaction rocket, I think it might be something along the lines of they call it antimatter catalyzed fusion pulse rockets, which I don't know. If we're going to get there, antimatter is extremely problematic, but right? And
why is it problematic?
I could go into reasons for antimatter rockets, but for this specific application, you're using a tiny, relatively tiny bit of antimatter with fusion bombs that essentially that you eject from the back of the rocket.
Prometheus?
I'm sorry.
That's the Prometheus.
Similar, but.
Yeah.
But so you're using the fusion explosions as a little putt of your engine to hit a pusher plate to send the ship going. I mean, this is something that we're not breaking any laws of physics here. This is absolutely feasible, and they've done proof of concept tests for this type of propulsion. And with that, you can get to 20% the speed of light. And if you don't care about cargo at all, you could potentially even get to say even 50% the speed of light using that type of propulsion. Of course. molecules and atoms in space getting in the way at that speed are hugely problematic. You got to get them out of the way, one way or the other. But that's kind of what we're seeing. And now, so this is a torch ship. Torch ships are fascinating. I'm not sure when or if we could even really get to a torch ship, but it's basically best of both worlds. It's highly efficient, like ion engines, and it's got really good thrust, like a chemical rocket. So torch ships are. What we will use with torch ships is not the Hohmann orbital transfer, where you're basically using, everything that goes into space now basically uses this Hohmann concept, where you're using
The least
minimum
delta
fuel,
V.
least
Yeah.
amount of fuel, the longest the travel time. How many times have you been pissed off? Like, what, this rocket's going to get to Pluto in how many years? Why can't you get there faster? No, because it's too expensive and you want a lot of cargo.
Orbital dynamics.
In the future, I'm hoping we eventually will get, instead of using the Hohmann orbital transfer, we're going to use the brachistochrome, which is essentially it's expanse in a lot of ways, where you would just accelerate. You accelerate at 1G for not like 450 seconds like a chemical rocket, but we're talking days, weeks, or potentially even months with this super high-end torch drive type of rocket. Imagine getting to the moon in 3 hours. Imagine getting to Jupiter in a week. That's potentially possible, although that extreme level of like you burn half the trip and then you turn around and you decelerate that's hugely expensive in terms of fuel. You don't necessarily want to do that all the time, but you could accelerate for a week and then cruise for a while and then turn around and decelerate, and that would be use much less fuel, and still your travel time would be so much better than anything we're seeing.
I'm sorry, you were still no, he was still going. I didn't want to cut him off.
I think that's a good ending.
Okay,
right
so
I just did the math on this, by the way. Just this past week, I did the math for Stuart. 1G acceleration, 4 days to Mars.
Yeah.
Home in orbit, 6 months.
yeah. And by the way, I'm sorry, go ahead.
3 days at 1G acceleration, 3 days deceleration, 18 days of coast to Pluto.
That's what we're talking about
Yeah.
here.
Now,
you had some thoughts.
yeah, I have a bunch of thoughts here.
We have limited time, so
could you
choose
tell?
wisely.
Could you
And
tell?
by
Yeah,
the
well,
way,
I
he
made
has
a list.
He has a theory as well.
Yeah, I don't know how many people will get that. Thank God. At any rate, first of all, if you're interested in exactly the logistics of this, I distributed some handouts earlier, or little postcards. That is the basis of most of the space travel in it, is exactly this sort of but first of all, nuclear. Even if we're not using nuclear as rockets anymore, you're going to use them probably as something which is your emergency or startup power plant. Because the thing about nuclear materials is it is on call until you need it. It is high energy when you need it. And if you need to restart, let's say a laser ignition fusion system, it ain't going to come from nowhere. You don't know you're going to have how long. Well, yeah, we need it in 2 days minimum. Yeah, well, the solar panels will get us the charge in about 2 months. So you need something that is actually going to deliver it fast. Nukes are in our future in space in one realm or another. I can't see a way around it.
Oh,
just yet.
nukes. I thought you said newts.
No, well, that's a
Nukes
different
might be
thing.
as well.
So here's
Looks
another
like
thing.
food source.
Yet another thing is that when it comes to fusion, right now we tend to think in terms of break even, because we're talking about power. You do not need break even to have an effective thrust agency.
Yes.
And that's the thing that people are leaving out. And you can actually do it. You don't even necessarily need the pusher plate, depending on how it's. You need the pusher plate. Something is going to have to sustain against that all those little pops. But the bottom line is, depending on how small you can make those little pops in the back, you actually are not you. There's always the choice of how much you're going to test the architecture. Where will energy come from? Where might we make antimatter? Okay, first of all, it's basically 10,000 units of whatever energy you want. Optimally, the best transition is for 10,000. Let's say whatever you put in watts. Let's say you'll get 1 watt back out of antimatter, because that is the nature of the inefficiency of it. How do you do it? Shackleton and Perry are the poles of Mars. They are essentially 24. They're like almost 24/7 sunlight, and about 98% of them are accessible. We are now making roll-out solar panels of things that are made mostly from silicates. What else is made of silicates?
Sand.
Well, the moon. I'm sorry, I said Mars. I said Mars. I said Mars. I meant the moon. The bottom line is the moon may be, because no atmosphere in the way either, so your efficiencies are higher. The bottom line is we may see. I think it's not unlikely that if antimatter becomes manageable and attractive, you'll see it on the moon and you'll see it gathered at the poles, the energy to make it. And the last thing is all of these things, the moment you get to anything like a relativistic in any way, like even 0.01 C, you are now dealing with exactly what Rob was talking about, which is long distance intercept of anything that would be big enough. I mean, you're talking about a particle having essentially the force of a tactical nuclear weapon if you hit it at that speed. There are ways around it. But this is where you're getting to staging. You probably want an advanced sensor ahead of that, and it has to be light speed communication to buy you enough time for a laser that is the length of your ship because of the focal length to pinpoint that thing and intercept it. And you better be right every time, and you'll be lucky if you get a half-second warning.
Yeah. This is where Star Trek's navigational deflectors come in. Very handy. They just kind of.
Let's just get on those.
Yeah, no problem. We're working on it.
I'm pretty sure that is the only time I've ever heard nuclear explosions called little pops.
Little pops, yeah.
I would just not like that to go
Antimatter
unnoticed.
enhanced fusion.
Yes.
Well, compared to antimatter, they're little pops. Let me tell you that for sure.
So, Rob, how are we going to protect our squishy humans as we accelerate at these kinds of rates? Is there like a magical juice I could pump in me?
Oh boy, I wish.
Well, there is. It won't protect you.
But the thing is, I also haven't heard anybody talk about more than 1G acceleration. So at that point, you're not really dealing with that issue yet. But if you're looking for more, then that's difficult.
Ideally, what you would want to do if you're going to subject the human body to prolong more than 1G, you want to suspend, you want to hibernate. And there's a couple of different ideas. You could actually...
Can we do that anyway?
Yeah. And Chuck is laughing because I wrote him some stuff for one of his...
I approached him for it. It's like, you know this stuff. And
yes, he twisted my arm because I was sitting in an ER one evening and getting all these texts from him.
Is that why you were in the ER?
Twisting my arm. No, I was just waiting. I was waiting.
Okay.
Waiting. And, but a couple of different things. Ideally, what we want to do is come up with some sort of a genetic modification. So we're going to gene mod ourselves to withstand higher gravity, reinforce our bones, reinforce our circulatory system. But we could do it artificially. Fluorocarbons are really good for that. And
Stay away from the chlorofluorocarbons.
yeah, we just stay away from the chlorofluors. But fluorocarbons are very good. We can use. We actually have some blood substitutes that are fluorocarbon based because they can still deliver oxygen. And if you had a fluorocarbon, basically liquid, you can fill the lungs with liquid fluorocarbon.
Exactly.
And you'll still get oxygen transfer. You don't breathe, so to speak. It has to be circulated. But the advantage you get then is if you can get rid of these air pockets that fill our bodies, then you can pressurize, and you can pressurize to be able to withstand a higher gravity force. But in terms of something like the juice from the Expanse, well, let's just say with probably just a really good vitamin water.
Well, and I think the important thing there, the reason that the fluid-filled lungs is helpful is that the fluid is incompressible. So it's not going. I mean, I'm assuming it's nearly water. Nearly incompressible, and so. The force on that gets transferred to structures around you rather than the body. And if your lungs are filled with fluid, then that too is incompressible. It's not going to smoosh you and make you chunky salsa.
Yeah, it's like the question of compression, decompression. And is what you really want is you want to get rid of the air bubbles, the air pockets.
All right, before I go to audience questions, we've been talking about probably realistic kind of things. Bob, give me a propulsion system that is way out there. Far future.
Black hole drives are out there.
No, they did that on Romulan
I
Warbirds.
return to
It's
the
fine.
fact
It's good
that
enough for the
A-bombs
Romulans.
are pops. Okay?
I mean, creating. I mean, this is It's kind of crazy.
Let's go there. Come on.
All right. First off, you create a black hole called the Kugelblitz, and you just got to get a lot of energy
German
and/or
word?
mass in the same spot at the same time. You could just use super powerful lasers to do this, and you could create a proton-sized black hole that is, first off, an amazing source of energy. You can get like petawatts of energy from this thing. So as an energy source that could last for years or even millennia, depending on how big it is. It would be amazing. Also, you could then feed it. You could feed it matter to maintain a specific size. You could use potentially the Hawking radiation as some sort of propulsion, potentially reaching half the speed of light with this kind of drive. The lifetime of the black hole, it could actually even get much closer to the speed of light. I mean, that's way out there. For me, antimatter rockets. Everyone has heard about antimatter rockets. I wanted to talk about that really quick. To me, that was always like the ultimate rocket because it's 100% conversion of
1 to
energy,
1.
right? So
1 to
you could
1.
go 99.99% speed of light. No, you can't. It was very disappointing to research this. Only 40% of the annihilation elements are actually usable. The pions that are charged, 40%. So that's
Lazy
I mean,
prions.
you've got gamma radiation, you've got neutrinos, you've got neutral pions that are, you can't, if it's not charged, what are you going to do with it? Gamma rays just go everywhere. It's going to radiate everything, so you need a lot of shielding, more weight, not as efficient. But using that potentially dealing with creating antimatter, we've created 18 nanograms of antimatter since the 50s. You could boil a pot of tea with it, with that much, but how are we going to create it? We're not sure how we're going to create it. We may never be able to create it. It's always going to cost way too much energy to create. Containing it, it's antimatter. Of course, containment's a huge problem. The radiation, so this, maybe we'll do this, but it's very problematic. If we do create it, I've seen numbers potentially getting up to 58% the speed of light, maybe in the 70 percentile. I don't think we'll ever get to 80, 90, 99% the speed of light using that type of technology. But there may be other ways to get that close, and that's another topic.
The relativistic effects of mass.
Yeah,
As
that-
you're getting up there, it's like, now
Infinite.
the hill's getting steeper
Right.
with every step.
But given enough time and an efficient source, a source that what you have to do is move away from reaction rockets to where the power, the energy, and the reaction mass is outside of the ship, like a light sail. Potentially, if you want to find out the absolute peak of possibility, using laser sails that extend not only the solar system, but throughout the galaxy, basically increasing, pushing on the sail, making you go faster and faster and faster. With
Stopping
super power,
becomes a
what
problem.
Yotta watt class lasers, I don't know what you
Yotta.
would need. But, I mean, you could potentially surpass any rocket you've ever heard of, fusion, antimatter, even black holes. You could potentially get ultra relativistic, 98, 99% the speed of light, if you travel long enough. And I'll end with a really cool thing about this type of propulsion. You could also, not only will it propel the ship, it will also clear the area in front of the ship. And it would also send power. You could send data over that beam. And if you send particle beams, it could send matter that you could just take the matter to use
now we just need
on your ship.
replicators.
So to me, from my research, that's the ultimate rocket, the ultimate drive that I've come across. And maybe we'll see it in many, many centuries. Kardashev 2.5 civilization might be needed. But that, to me, that's the ultimate I found. That's plausible. All right.
As a former laser physicist, I ask you not to stare into the Yotta laser. All right.
Can I-
So we are now ready for audience questions. What we're going to do, because it's hard to keep track of everyone, we're going to go section by section. Way over here, audience right, audience center, audience right. Or are you starting over here? You're already over here. All right, I won't make you start to run, but we'll go section by section. And audience, if you can, if someone has been trying to get their hand up, please help us know that, this person has been trying to ask a question for a while, because there are lots of you and there are a few of us, and we are scared of you.
You can always try a wave.
All right.
Did we just do a wave?
Yeah. Mini wave.
Mini wave and celebration.
I just wanted to know, have we given up on the Alcubierre drive?
Yeah.
Does somebody want to explain that?
You
Just make a space-time bubble. That's an
yeah,
easy
no,
thing.
it's fine. It's in the same realm of possibility as no, it's not.
No.
It's not a thing.
It's very cool math. It would require particles of matter that we don't have. Like, let's start by making things with negative mass.
Yeah.
Sure. To invert space-time.
Yeah,
And
exactly.
I definitely wanted to, when we were talking about drives, and since you asked about drives, I definitely want, anytime this comes up, and Aaron's not on the panel, I definitely want to put that forward, warp drive, okay? Right, Star Trek, okay, it's a plot device, sure. But people have done the calculations, and I credit Aaron McDonald with all of this information. They did the calculations to see if you could use, a warp drive to, shrink space in front of you and make it bigger behind you. It's warping space. When they did it with an ellipsoidal thing around, like the Enterprise D's shields, when the Enterprise D gets hit, it's like an ellipsoid. That amount of energy that was needed to do that was all of it. And when I say all of it, we're talking about E equals mc squared, kind of that level of energy in the universe, like all the matter in the universe.
Well, the observable universe.
I mean, yeah, we don't have to count the part that's going away faster than the speed of light. Now, when those calculations were further refined to be more form-fitting and shapely, like the shields of the Enterprise in Strange New Worlds. Yeah, I'm getting some Star Trek in there. Okay, you can see, I'm a fan. All right, so it was, now you would only need the energy from the mass of a semi-truck, which sounds small, but it's not. We cannot convert that amount of energy. And the last thing I saw was that people are still doing calculations on this. It's not out of the realm of possibility yet, but instead of, say, the Enterprise, going this way with the thin aspect going forward, it would need to actually go this way with the saucer like vertical to the direction of travel.
Oh, that would not look nearly as
I
cool.
know, but the calculations are there. They've done them. Okay, go ahead.
Excellent question.
So my question is, you talked a bunch about the future of nuclear drive or nuclear propulsion. I'm curious, what does the first nuclear drive look like? What's that going to be realistically if we build it, which hopefully we will?
Already been built.
Nuclear thermal propulsion, essentially twice the exhaust velocity, half the trip time. That's 450 seconds specific impulse. That's what we're going to be looking at in the next 10 years.
Google NERVA and prepare to have your jaw drop when you realize it was achieved in the 70s.
Yeah, and also the prototype is sitting at the U.S. Space and Rocket Center in Huntsville, at least last time I checked. And
no one's stolen it yet.
No one's stolen it yet. And
Exactly.
I lost it.
Now there's a novel idea.
Novel.
Exactly. Someone steals the Nerva prototype.
Rocket heist.
We're going to need to talk to you after this session, Dr. Hampson, and prepare for an extended stay in an undisclosed location.
And if any of that happens, we'll ask you about it here on Ask Me Anything.
Everybody wave at the camera at the back that is filming everything they just said. So, section over here. Oh,
Quick question for each of your favorite propulsion type. What kills us first?
Alzheimer's disease.
Okay, so favorite propulsion type. Right now, mine's electric. Time. Yeah, time kills us. Radiation for you?
Anything that's high radiation,
Mhm.
it will be the neurological consequences.
Absolutely. And we do have the research on that now from, you correct me if I'm wrong, but from folks on station. I think it was specifically, of course I've lost their names, the twins.
Yeah, the Kelly twins.
Yes, the Kelly twins. The neurological, cognitive impact has been documented in that, I hate to put it this way because they're awesome humans, but it makes you dumber. It makes you less cognitively capable.
Well, that it was my entree to space sciences, was radiation effects on the brain. So yes, it's a lot. That's a totally different lecture for another time. So tell Stephen or tell Rain that you want that next year.
And listen to it before you go to space.
Bob?
I'm having trouble with the question. I mean, a propulsion, pick a propulsion, and then how that propulsion is going to kill you?
Yeah, pretty much.
Yeah. Do you need a minute? Or?
All right, chemical rockets die of boredom.
Or G's.
So
or
down on
G's.
chemical rockets.
Or G forces.
Chuck?
So since we've already talked about radiation, which I think is going to be the higher the energy release you're talking about, the more likely that radiation is involved. So I'm going to assume that has been handled. That death, we've already defined that. I think the next is any loss of control in any of the major subsystems, because the bottom line is you are piping so much energy, and it may be not the radiation from the drive, but itself, but actually the power plant that's generating the lasers or the energy in the containment, the tokamak sort of style thing, any of that stuff, that plasma gets out. You are talking about massive destruction. And I'll point out that one of the things that makes it more deadly is the fact that you're really going to always be looking at, this is a game of mass. So always you're looking at light frames. You talk about, first of all, you have now side vectored in a major way. And the thing is that there is so much destruction, and how much will a fairly, you think about a long keel craft, think a lot of things lined up on it. You start pushing a side vector in, you don't know all the things that could be breaking, and that you won't know right away necessarily either.
Start decelerating.
I'm going back to Bob's Yottawatt lasers. Beam drift. Pointing those things accurately is going to be a whole lot of fun, so that you hit the sail and not like where the humans are.
What really happened to Aldebaran?
Well, I'd also like to say that my current, and throughout most of my life, my current favorite propulsion method is the Space Shuttle main engines. One of the most efficient and high thrust to weight rocket engine ever built. And there are 3 of them on board Artemis. Hey, by the way, a third
Breaking
troubleshooting attempt to resolve the hydrogen leak has not fixed the problem, and they're trying to figure out what's going on, but my guess is it's not going to happen
Scrub.
today. Yeah. So hydrogen will kill you if you're not careful.
Yes.
On Earth.
You guys spoke in terms of 1G accelerations and stuff like that. Lesser accelerations will get you almost the same effect and maybe a lot easier in terms of reaction mass and stuff like that. Correct? I mean, that's what I seem to have gotten the impression of.
It's a parametric trade-off.
If you take a look in Heinlein's expanded universe, he actually gives the numbers of, I think, 0.1 or 0.01 constant thrust. But you can take that as a couple of weeks or something like that, and the entire solar system's in range. And we're not talking about range in years. We're talking range in months.
But
max.
don't forget to slow down.
Yeah, so it depends on your patience.
That is with counter boost.
Gotcha.
But then you're dealing, of course, with the effects of low gravity, which we don't know yet.
Mm-hmm.
Yeah.
Could you guys expand a little bit about spaceship-length lasers intercepting particles? And, for example, we have this thing called Whipple shielding on current ISS type stuff to protect from micrometeorites. Is that technology just totally unfeasible once you're going a certain speed?
So I'm going to start and I'll hand it off. But the basic premise there, and it's something we use today in keeping satellites in the orbits that we want them, is solar radiation. For satellites right now, it's solar radiation pressure. What that means is that while photons have no mass, they do have energy. And most of you know that E equals mc squared, but the extended version of that is E equals mc squared plus pc. P being velocity. Being momentum and times the speed of light. So even if you don't have mass, the energy equation says you have momentum. So when a photon bounces into a surface, conservation momentum says that momentum gets transferred. And you get enough photons bouncing against a surface in the same direction, it's going to affect the position velocity of the spacecraft because there's very few other perturbations out there.
If it bounces off, it's twice the momentum, right? Rather than being absorbed.
Right, it's not usually absorbed. It's usually it depends, I guess.
Right,
so,
depends.
Yeah, totally.
Absolutely.
So you get a Yottawatt laser. Yotta is that's probably one of my favorite prefixes.
It's up there.
Yeah, and we never get to use it.
It is literally up there. Yes.
Yeah, but that means really large. I know it's a 10 a.m. panel, so but it's a really large amount of photons hitting in the same spot and in the same direction. That's basically what's going on.
So, and the reason you need the length is because laser power is generally related, at least as we've been generating. But I'm sitting next to the guy who's going to either nod or shake his head with a merciful roll of the eyes. That your concentration of beam and the energy you're delivering in the beam, which is going to diffuse no matter what you do, is a function to some degree of the focal length, the energy you can put into it, and the focal length of essentially the concentration of the light. And that is going to be the only thing that's fast enough to when you're talking about, when you're getting into, the moment you start attaching the letter C to the back of anything, unless you want like 9 zeros in front of it, you are talking about something that is moving so fast that you're going to have, like I said, far lookout to be able to get that thing targeted and fired in time to hit that little tiny bit of space.
No Whipple shield will protect you, right?
Those things aren't rated for anything, like, because you're looking at remember, you are the velocity, and it may be moving, so you may have other effects, but the speed at which you're moving turns tiny amounts of matter into deadly bombs.
And you really do not want that coming into your craft, any kind of physical structure.
Yeah. Bearing constant range closing is not the report you want to hear.
I think at low velocities, like say maybe 0.1 C, I think you could just have a shield, a nice shield in front of you that would be ablated as you're traveling within the solar system, and then you'd have to kind of fix that and repair it. But once you get up above, I think it might be 0.2 C. Then even that's not enough, and you need to clear the space.
Deflector
And
shields.
since our question came from somebody wearing a pure and clean ice mining uniform there, so a great big iceberg would be useful, but only, as you say, up to about 0.1, 0.2 C, because then what you actually get is, if it's traveling in a, say, co-velocity, it's not actually attached to your ship, then yeah, ablation is great, but all those impacts are going to start pushing it back toward your ship. And
you have to
and
re-accelerate
eroding
it.
and you've got constant low-level explosion going on the face of this.
Yeah, and it's
Just pushing
creating
it
a
back.
debris field into which you are heading.
Oops.
So yeah, so lots of some issues there. Yeah.
All right, we have time for one last question over here.
Oh, okay.
We don't have anyone over here.
I thought we did.
Oh no, we have several people. Actually, you had your hand up very early, so thank you for reminding me.
So my question is about how far are we away from, right now we have to always design as a dual engine design. We have to have a chemical repellent to get away from a gravity well, but then we have something that's more sustainable to get us up to speed. Is that ever in our short-term future not the case?
Chemical rockets, we're going to be launching from the Earth with chemical rockets for the foreseeable future. Nothing really matches the thrust. I've only come across one instance where we may be able to create a nuclear rocket that could potentially have enough thrust to actually launch, but it may spew a lot of radiation. I mean, chemical rockets are going to be it for a while, until maybe we create orbital rings where that can then use some sort of elevator to go up. Not a space elevator, but an orbital ring,
say, I'm still not
which will be
sold on
much lower altitude. But yeah, we're going to be using rockets to get off. But once we get off of the face of the Earth, that's it. Then chemicals will be
Look up SLOUGH, SLOUGH, and Jean-Luc Cambier, who was at Edwards Air Force Base. There was a project which was essentially, but again, it sounds great, but there's the catch on the end, which is essentially you're talking about largely magnetic bottling of plasma, and you release that at very high velocity. Not fundamentally a rocket idea. Now the question is, how are you doing it? Well, you're back at a nuclear rocket, because that's where the energy is coming to both heat the plasma, keep it accelerated on all the rest. Now, the material science, which even since that was done, and it was being introduced largely as an intercept vehicle for planetary defense, we're going back to this was a Sigma thing in 2008, 2009. Material science has gone forward in such a way that what's happening with every step forward, the mass required for the vehicle because of the change in the composites is actually making it more and more feasible as time goes on. But you're still, you got the question of, Where's the energy coming from? And right now, we got one answer for it, and it's called nukes. Now, you put that in orbit, and now if you have, a fusion plant, you can essentially turn it into a drive. You may have other ways of doing it, but right now, you
Again,
want high energy
nukes,
travel.
not newts.
Yeah, nukes.
And by the way, I think recently there was a relatively successful test of the, what is it? It's spinny yeetatron. Yeah. And they successfully yeeted something very small, which I didn't see that being successful, but okay.
But very, very high G's. You're not going to be locked in units with that.
Yeah, that's cargo.
One of the other ones that was experimented with, where are we now with lasering a reaction cavity underneath a spacecraft? You have a capsule that is nothing more than a concavity, and then you beam a laser and boom.
Another one is if you have enough energy, you could look at, and depending on the size of construction you want, and that's in one of those tests is in this book, is an equatorial mass driver. Particularly if what you're talking about is launching something that has a boost bus that will come off it. So in other words, don't try to get to orbit just on the first kick. Get it high enough up that then a disposable booster puts it in orbit. Once again, you will not put anything that could get turned to jelly will get turned to jelly, so you're not putting it in that. But anything else,
we call it pate.
Yeah.
But to answer your original question, we built the International Space Station. Admittedly, a space shuttle was a huge part of that, and it has propulsion, but not a lot. But it was also a proof of concept that we could build things in orbit. So there's no reason not to do that, and frankly, one of the reasons to do that and to go to the moon and have a base on the moon is because everything is easier when you've either already accelerated to that speed, and then you can you fuel up with whatever from the Earth or from the moon, and then the moon's got 1/6 the gravity to overcome, right? And then you go on your way.
And whoever hasn't heard of the terms L4, L5, and L2, those are going to be in your future.
Yeah.
Interesting fact: if the Earth at its current diameter was 1.5 times more massive, chemical rockets would not work. We would not be able to launch anything from the Earth if it was that much more dense. So, interesting implication for extraterrestrials if they live on a dense planet. They can't use chemical rockets to launch. So interesting to see how they would evolve and get stuff in orbit. Eventually, they could probably do it, but not good. So that's just an interesting fact I came across.
All right, we are at our end. Before we end, we're going to start down with you, Andy, and we're going to come this way. Tell where people can find you online, and if you have, books to wave, please wave them. So, Andy, where can people find you?
I don't really do that. I mean, I do, but I don't do it professionally.
Space Track. We can find you at Space Track?
Space Track. Across the hall, Monday morning, 10 a.m., Space Shuttle. It's just me talking about one of my favorite things. So, if it's your favorite thing, too. And I think there's another. Is there another one today?
Check your badge.
This was it. This was it until Monday morning. But that's where I will be Monday morning, 10 a.m. Please.
Okay.
Rob.
rehampson.com, rehampson.com. Also, several more science and space track. And Bain Books. I've got a signing at the missing volume at 1 o'clock, and a new book coming up, which is a treatment of the $6 Million Man, but written by somebody who actually participated in the DARPA prosthetics program. And so that'll be coming out
more than $6 million.
Excellent. Bob, do you have something to wave?
Yes. Skeptic's Guide to the Future. Book.com, or just come grab this. I got a bunch of these. Come grab them if you're interested in pre-ordering. It's going to be released in a few weeks, and it's a real fun read. I think everybody here would really enjoy it. Thank you.
If you've been interested in even one, probably 80% of the stuff that I've talked about is actually in the first book in this series, which is the Kane Riordan series. I have multiple signings. Just go to the app for that. I have, and if you won't get there, and if you want to find out how to find it, it's here. The last appeal to that is, as Bain frequently does with series, the first book actually is a free ebook. So it's the crack cocaine.
I was gonna say
strategy of book selling. The first hit is free. After that, it's full freight. So there you go.
Don't forget to rate
I'll
the
stay
app.
up here or go out there and pass these out.
And finally, I am on Twitter as Sargent, Sargent, for reasons that are too silly to explain.
Indeed.
Where you can find a link to the newsletter that I put out every 2 weeks talking about science and video games and storytelling. So please thank these awesome panelists. Oh, wait.
And no, before you thank us, this guy Steven does a huge amount of wrangling. We wouldn't be here if it wasn't for him. The applause.
To that end, please be sure to rate the panel in your app.
Yes, if you have feedback, and hopefully it's good, put that on the app. The powers that be pay very close attention to that. That is what lets us, for example, get extra room to put all of you lovely people in here. Thank you so much for coming. Have a wonderful con.
All right, folks.